In this video, we'll answer a question: how do CPUs work? When we're staring at our computers all day, like right now, many of us take for granted how it actually works on the inside. Even if we start learning programming, what happens behind the scenes is still unclear. Code we usually write is high level, stuff that is intuitive and English-like to us, but gibberish to the computer. Every time we run a program, the compiler converts this into a language the computer can understand. But what is really going on there? Back in the age before computers, people had to do all calculations by hand, including the multiple-hour military calculations needed for World War II. A guy named Alan Turing started thinking if it was possible for a machine to do all these calculations needed given a set of instructions. In 1936, he published a book detailing something he dubbed a Turing machine, a theoretical computer. This machine has an infinitely long tape consisting of many cells, known as registers, with data, like a number, and a virtual head pointing to one of those cells. At each iteration, the head reads and changes the data of that register or jumps to a new location, and the cycle repeats. The virtual head is controlled by a program of instructions that tell it what data to overwrite or where to move. How does performing these seemingly elementary and pointless operations create cool, large programs? If you think about it, all computer programs use a huge set of instructions, like a user-defined instruction to check for collisions in a game, or a commonly used inbuilt instruction like a loop. These instructions are high-level. They're embedded deep inside many layers of abstraction, so we can break them down to simpler ones. Collision detection can be reduced to a combination of comparison operations for each of the coordinates. After many layers of abstraction, we reach a point where instructions are so simplified that they are nothing more than simple operations like add, bit shift, and, or, and input-output. As we will see later, these instructions can be understood by the computer and are easy to implement. Stepping back a little, we recall that this Turing machine is theoretical, but how can we implement this into a physical, concrete computer? Another guy named von Neumann saw the potential in what this Turing machine could accomplish, who knew the importance of a stored program of instructions, and that the computer was doing nothing more than logical functions. So, he was influential in creating the von Neumann Architecture in 1945, an implementation of this Turing machine which almost all modern computers use. Okay, so how exactly does the von Neumann architecture work? Let's look at a step-by-step example of a single accumulator-based CPU architecture. Before we dive in, recall that many parts of this architecture involve many registers that could be thought as little memory cells. Represented by little boxes, they contain an address, which is sort of like a location that one can find. Each of these register boxes contain a value, which can be retrieved through the register's address. Okay, first we have a program counter register, which stores the address of the current instruction. Since the program counter contains the value of 0, we retrieve the instruction from memory with the address 0. Then, the PC increments 1 so that it can read the next instruction in the next iteration. In this example, instructions have a format, where the first number represents the opcode of an operation and the second the operand. The opcode refers to each instruction's unique key. An opcode of 2 refers to the load instruction. An operand of 7 tells the computer to load the register with address 7 into the accumulator, which is a temporary storage place for calculations. It's like a regular register for memory, except one can perform operations on it. Then the cycle repeats. The program counter tells us to go to register 1, which yields an opcode of 1 and an operand of 8. The PC is incremented by 1. Register 8 has a value of 3, the accumulator has a value of 4. Opcode 1 refers us to the add function. So we need to somehow add 3 and 4, but where would the actual addition happen? Turns out there's a thing called the ALU, or an arithmetic logic unit, which handles all mathematical and logical instructions. In essence, the ALU is a function selector that takes in 2 inputs, chooses the operation, and spits out the output. So, we're actually going to take register's 8 value of 3 and the accumulator value of 4 and plug this in to the ALU with the opcode as the function selector. Since 4 plus 3 is equal to 7, the ALU outputs this value and stores it back into the accumulator. The program counter is at 2, and register 2 has opcode 3 and operand 9. The store instruction tells us to save the accumulator value back into memory at register 9. Continuing this pattern, the computer will be able to solve any computable problem given a large enough instruction set and enough memory and time. This is the basic idea of how a CPU works. Of course, input from mouses and keyboards and output to monitors and the like would be added, and there would be many layers of memory. And optimizations will be implemented for efficiency. This kind of sums up what machine language is: a program of basic instructions decoded and executed by the CPU. Of course, there are many variants. Most CPUs use a lot more opcodes, and some have multiple registers for calculations instead of one accumulator. Finally, a less used Harvard architecture and hybrids exist as well. But this video shows the basic idea.